Okay, so this is the section on this is actually going to be kind of a long section because we're talking about the electrical signals, uh, and specifically we're going to start getting into ion movement. So we get to apply some of the chemistry that we talked about specifically when it deals with ions, which are charged molecules like sodium and calcium and chloride and potassium. Those are the main ones we're going to talk about the rest of this section anyway. Okay, so I'm going to try to get through this fast, but it's a really, really important part. And by fast, I mean it's going to be long, but I'm going to go as fast as I can. So the first thing is that most cells, and this is true for neurons and it's true for really any cell, they tend to be negatively charged on the inside of the cell. So if we draw a neuron here and we have our dendrites, this is a very bad neuron, I know, but if we have our dendrites, we can see that if we were to measure this, we would see that the inside is about minus 70 millivolts. Now, the reason for that is a lot of different things. First of all, proteins. There are lots of proteins in there, and those all tend to be negatively charged. Um, DNA tends to be negatively charged. And so that contributes to the negative charge. But there are a couple of other important things about maintaining this resting membrane potential. And that is that there happens to be a lot of potassium on the inside of the cell. And there's a lot of sodium on the outside. Okay, so this is true for every cell, just about every cell in your body. This is true. This is homeostasis. This is where they like things. So if we get rid of the neuron and we just draw this as a cell, okay, we can still think of it as a neuron, but it's just much easier if we have it as a big circle. And we say that it's minus 70 millivolts on the inside. The way that potassium, first of all, potassium, if you ask yourself this question, sodium, do you think sodium wants to go in the cell? It's negatively charged on the inside, and sodium is at a high concentration on the outside. Okay, so you would say, yeah, you know what? It's positively charged out here compared to the inside. It's negative on the inside, so sodium, opposite charges attract. So sodium wants to go in, but it's not allowed. Okay, so it wants to move down its concentration gradient and its electrical gradient. It wants to move in because it's negatively charged. But then if we step over here and we say, well, what about potassium? Well, you would say, well, yeah, potassium wants to move down its concentration gradient because it's a high concentration inside the cell, but it's also negatively charged in here. And so potassium's going to like that. It likes that it's minus 70, right? But the thing is that potassium, and that's absolutely true. Potassium's really not sure in some ways. But if you measure the concentration of potassium in here, you can actually do a calculation. It's called the Nernst calculation, that we'll talk about to calculate something called the Nernst potential. We can actually see that at this concentration gradient, potassium would actually like it if it were minus 90. But it's not minus 90, it's minus 70. So potassium wants to be a little bit more negative. So yeah, it's not quite negative enough for potassium, so it kind of wants to go out. And so this concentration gradient is one of the things that maintains the resting membrane potential, because the the membrane is a little bit leaky to potassium, so some potassium can leak out, and it does. It's constantly leaking out. But the thing is, we also have something called the sodium-potassium pump. What the sodium-potassium pump does is it pumps in 2 potassium and at the same time pumps out 3 sodium. So it is what is this concentration gradient of a lot of potassium on the inside, a lot of sodium on the outside. It is the sodium-potassium pump, or sometimes called the sodium-potassium ATPase because it burns ATP, that is constantly pumping out 3 sodium and pumping in 2 potassium. And then the potassium's in there and it's constantly leaking out. So this is like a cycle that's happening all the time. And at homeostasis, when everything is working properly, this cycle keeps it maintained at about minus 70 millivolts. So if you've heard about potassium or if you've thought about potassium, it's probably, my guess is blood potassium levels or bananas. You have to eat your bananas because they have potassium. And that's exactly right. Not necessarily bananas, but that you need to have the right amount of potassium. If your potassium levels get too high, if your extracellular potassium levels get too high, well, this potassium's not going to leave anymore. And if the potassium builds up in here, this is going to go up to like minus 60. It's going to actually, if it started out, if we graph this and we say this is minus 70 here, okay, so if we graph it here, and we say this is our resting membrane potential, and then we say all of a sudden potassium stops leaving, it's going to start going up and it's going to become less polarized. Okay, so polar, remember, polar is a charge differential from one side to the other. So if this is positive on the outside, negative on the inside, with a change normally of minus 70, we say it's a polarized membrane. So this becomes slightly depolarized. Okay, so this potassium, your potassium concentrations have to be just right. And if the opposite happens, where there's absolutely no potassium out here, because there's always a little bit, then what's going to happen is this potassium is going to want to leak out even more, which is going to, we call hyperpolarize the membrane. So yes, it's very important that your potassium, blood potassium levels, that you have the right amount of potassium in your bloodstream at all times, because your bloodstream is also your extracellular fluid. Just it's blood and extracellular fluid are pretty much the same, except there are no blood cells in your extracellular fluid. It's the same fluid though. Okay, so resting membrane potential is determined, and this will be a question on the test if nothing else. It's determined by this potassium gradient and the function of the sodium-potassium pump, but also the permeability to these ions, potassium, sodium, and chloride. Now, the thing to remember is that this is not very permeable to sodium. There's some sodium that gets to leak in every now and then, but not like potassium. Potassium actually, the cell is actually not very, but a little bit leaky to potassium. Way more leaky to potassium than it is to sodium. So that's the permeability. It's a little bit permeable to potassium. And it's that constant cycle of going in and out and going in and out that maintains that inside or electrical gradient, membrane potential of minus 70. Okay, so I hope that makes sense, and it's very easy to change, and that's why when you go into the doctor, or if you end up treating someone, that's one of the labs that will be done is to figure out their blood potassium levels, because that can really make a difference that we'll see later. Okay, so this is what I was talking about with the Nernst equation. You don't have to do this equation, especially when you see a logarithm. A lot of people, myself included, kind of panic with a logarithm. You think, well, gosh, now I have to actually think about this. But it's easy. You could type this into a calculator, and you could type in the concentration of potassium on the inside versus the concentration of potassium. There's a little bit out here on the outside. And if you were to calculate that, you would see that at that concentration, potassium wants the cell to be at about, well, minus 90. And that's what we see. If we do that calculation up here, we see that when we calculate it, it's minus 90. But that's not, again, what the membrane potential is. It's minus 70. And that right there is why, if we give it a chance, which we do, they're called leak channels where potassium is allowed to leak, and it constantly is leaking out. Okay. Now there are also sometimes you can open a channel and potassium will just rush out. Okay, and that can actually well, if it leaks out, that would really hyperpolarize the cell because you're losing all this positive charge. Okay, so, and if we look at sodium, because remember, sodium, we'll go ahead and leave that guy out there. Sodium, if you recall, is higher on the outside of the cell. And sodium will rush in until until the inside of the cell is plus 60, which isn't going to happen. A cell doesn't function at plus 60. It might make it up to like plus 30 or something, but so sodium is always ready to go in. It always wants to go in. Okay, all you have to do is open it up, which most cells are not very permeable to potassium. I just erased my whole cell. Okay, so so that's it. That's what the Nernst equation is. You just kind of have to know what the Nernst equation is. It just kind of describes this membrane potential, and it focuses on a single ion. Okay, if it were only permeable to that ion, and that was the only ion that existed, then that's what the Nernst potential tells us. Okay. So the membrane potential is influenced by the concentration gradient and that permeability. Now, the Nernst equation just looks at a single ion at a time, and that gives us a lot of information. That's how we know that really sodium or potassium wants to get out. However, if there's another equation here that you see in your book, and this, of course, you clearly don't have to do this one. I wouldn't even know how to give you all of the concentrations. I suppose I could, but I don't want to. But this is called the GHK equation. Goldman Hodgkin's Katz, that's what that stands for. And that takes into account everything, the permeability and the concentration. Those little square brackets mean concentration of the inside versus the outside. So you could painstakingly go through and put the concentrations of everything, and it would give you, and that's what this is, your membrane potential. Okay, so we don't have to do that. We know that it's about minus 70. We've measured it. People have measured it, and we know that it's about minus 70. Some places say minus 65. Some places say minus 75. But minus 70 usually works. Okay. Okay. So hopefully this makes sense. We have a cell that has, and we'll pretend this is shaped like a neuron, that has a lot of potassium on the inside and a lot of sodium on the out, or a lot of sodium on the outside. And it has a resting membrane potential of minus 70 millivolts. Okay. Now, what can we do with that information? Well, one thing we could do is we could change it. We could say, oh, what happens if we make it permeable to sodium all of a sudden? Well, if we make it permeable to sodium, sodium is going to rush in. It's going to take that positive charge with it, and this is going to go from being minus 70 to something higher. Let's say minus 40 or minus 30 or something like that. So if we were to graph that, we would see that it would go from being a minus 70, it would suddenly go up. Okay? All right, so this is how cells work, and this is how communication works, and we're kind of going slow, but because what we want to do, remember, ultimately our goal here, that's one of the purposes of this section, is we want to figure out how a message can get from here. Let's say a neuron comes up here and says, hey, you need to fire. So this neuron brings a signal down, releases a neurotransmitter. Let's say it makes it permeable to sodium, becomes positively charged, but that signal is going to fade. Okay, and so it's not going to make it all the way down here, because what we ultimately want to do is we want to have an action potential. And that's what that's called, and we'll talk about exactly what an action potential is. But this is our goal, is to depolarize the cell, so make it more positive or push it towards positive. We want to depolarize the cell so we can activate it, so we can make this one release neurotransmitter and keep that signal going. Okay, so that's what's trying to happen. So I just mentioned depolarize and hyperpolarize. Now, if you let sodium in, or you let something positive, I guess it doesn't have to be sodium, it could be calcium, but if you let a positive charge in when it's sitting down here at minus 70, and all of a sudden we'll just draw it as a circle again, all of a sudden you make it permeable to sodium, then all of a sudden this minus 70 is no longer minus 70, it's minus 60 or it's minus 50. So that's what happened in this case. We have and that's what that's called. We have depolarized the cell. It used to be polar, very polar down here at minus 70. We've depolarized it. We've taken it all the way up to what I guess would be minus 40. Okay? Now, what if instead of sodium going into the cell, what if we decided we were going to let chloride into the cell? Well, chloride is negatively charged. Well, chloride, if chloride is allowed into the cell, it might go from minus 70 to minus 80 or minus 90. Okay, so it's going to, and what we call that is hyperpolarizing. In this case, it looked like, so this would be like if we were to let chloride into the cell, then what it looks like here is it went down to, I guess that would be minus 80. Okay, so but it went from being minus 70, it became more polar, it became hyperpolar. So that's hyperpolarization. Okay, so I hope this makes sense because we're moving into how all of this is going to work and what we really need to know about all this. Okay, now, so when we let that sodium in, so if we focus on this at first, I'm not too worried about this graph. This just means that at 0.0, I might come back to that. But if we, at this point right here, all of a sudden made it permeable to sodium. So this came down and it said, hey, talking to this neuron, it says, hey, you neuron, I want you to fire now. I just fired, so I'm going to release some neurotransmitter. It binds to this little channel, opens it, and now sodium rushes in, and it depolarizes it. But here's the thing. In this kind of a situation, the sodium, yes, moving in will depolarize it, but it fades. It fades over distance, okay? So we call that, it's listed here, and it's listed here, we call that a graded potential. Okay, so a graded potential just means that it's a local signal, it's current flow, okay, and it fades over time. What happens to it? Well, it bumps into some other things. It might bump into some other molecules. There's lots of stuff in the matrix. It might just leak out. That's what you see here. The signal is just sort of leaking. It might leak out up here, but it goes away. And so it's very, very strong right where the sodium is coming in, obviously, because that's where it all is. But then as it kind of dissipates, it moves out and it kind of goes away. And that's what this graph is showing. Further distance away from it, the more that signal fades. Okay, and we call that a graded potential. And that takes place usually in the dendrites and the cell body. Okay, so that's where you see graded potentials. Okay, and that's what this is. That's what this is sort of listing. So remember our goal here is to get that signal to move down the axon. Well, first of all, we have to get it to the axon. And if it keeps fading, it's not going to get it there. So there's something here, we call that a trigger zone. And that's where we have that's where the signal has to be. So that's where that depolarization has to be. So if it's sitting at minus 70 normally, we're trying to get it up to what's called a threshold. So if we're looking at this area here and we're saying, oh, we're trying to depolarize it, but our signal keeps fading, well, that's what we're trying to do is we're trying to get it up to a threshold, which is usually minus 55. So it's sitting at minus 70 resting. We're trying to get it up there, but we just don't know if we can make it. And if we do make it, then we send something called an action potential down the axon. Okay? All right, so local current flow, and that's what this is a wave of depolarization that moves through a cell. usually, like I said, the dendrites in the cell body. Okay, so wave of depolarization. Graded potentials lose strength, so we've discussed that as they move through the cell due to current leakage and cytoplasmic resistance. That's just all the stuff that's in the cytoplasm that's causing it to fade as it moves through. Now, we might be able to put another one here, and that might bump it up enough, and that might get it up to threshold. So they can be summed together. So that's also kind of an important thing. If it's strong enough, the graded potential will reach the trigger zone. Okay, so we drew that here. We said that that's right here. It's called the axon hillock. That's what you call that. The very first part of the axon is called the axon hillock. And if that's the case, then you can actually get an action potential to fire, and we'll talk about what an action potential is, but it really depolarizes. An action potential does. All right, so I just mentioned that maybe this guy could get a little help, but you know what else? Just erased all of him. You know what else? It could also be hindered in a way. So what if this one, we made that one leaky, this up here made it leaky to sodium. What if we made it down here leaky to chloride? Well, chloride's negatively charged. So that means that would actually, instead of being exciting to excite the neuron, that would actually be inhibitory, and you would be inhibiting the signal. You would be hyperpolarizing. Okay? So that's where we get these two terms. Excitatory is going to depolarize, and inhibitory is going to hyperpolarize. Okay, so we just covered those terms, and that's where it all matters. So when we're talking about graded potentials, the biggest thing to remember is we're talking about in the dendrites in the cell body, because when it goes down the axon, that's called an action potential. Okay, and we're talking about letting in charges, letting in the sodium to make it positively charged, or chloride to make it negatively charged, primarily. Okay, so if we come and we understand that stuff, then we can look here and we can say, okay, we can redraw this whole thing. Here's the incoming neuron that's saying, hey, talking to this guy, talking to this one, saying, hey, I want you to fire. It depolarizes it, makes it leaky to sodium or whatever. It's usually sodium in this case. So it makes it leaky to sodium, and then the signal fades. So right here, where the neuron first opened the channel, oh, it's easily. So if this is our threshold, if that's our threshold, this is easily over threshold. However, because it fades, now it's at threshold, and by the time it gets to the trigger zone, it's below threshold. So nothing happens. No action potential. This wasn't a strong enough signal to make this neuron fire. So this neuron does nothing. The signal dies right there. Okay? Now, but what happens if it does? What happens if the signal is big enough, or maybe, there are a couple of neurons coming in there depolarizing it. But what if somehow the signal is big enough, huge stimulus in the beginning, up here, and then in the middle it's still fading, but then when it gets to the trigger zone, it's still above threshold. So you still have a signal. And if that's the case, if you get to the trigger zone or the axon hillock, if you make it there and it's still above that threshold, you will have an action potential. And this neuron here will fire as well. Okay, so that's kind of the goal. And now you can do that. Like I said, I mean, even this one, if we go back to the previous one, we might be able to do something like, we might be able to have another neuron that fires here that lets the sodium. I started to draw that depolarizes, and then that might help make it strong enough. But yeah, that one all by itself didn't do it. This one, it did. We were able to get past the threshold, over the threshold, and then fire an action potential. Okay, so that means we've moved. We've moved on. We got beyond the graded potential, which is happening here in the dendrites in the cell body. We've managed to get our signal to the axon. Okay, so now we want to fire an action potential. So you may ask yourself, well, how does the axon hillock, or how does the trigger zone, how does it know what the voltage is? How does anything know what the voltage is? There are little things in there called voltage, it's supposed to be a V, voltage gated, here I'm just going to write it all out once. Voltage, because they're really important, gated sodium channels. Okay, what that means is that when, this is why the threshold even exists, this is the threshold, when the voltage changes to a certain point, there are little channels that are sitting right here, all along here, that when the voltage changes, they will open up and become permeable to, guess what? Sodium. So they're gated, oops, I said gated and started to write gated. They're gated by sodium, okay, or by voltage. They're gated by the voltage change, but they let sodium through. And when that happens, okay, so if you go back to the graph and you look, okay, you had your graded potential that made it all the way there. You hit threshold, and now a bunch of sodium channels open up. This is going to just shoot straight up, okay? And it's going to completely depolarize the cell. It's almost like positive reinforcement. It took a little bit of depolarization, and then it became even more depolarized. Okay, now I'm going to kind of jump ahead here. Just to let you know, it doesn't end there. It then repolarizes very, very quickly. The repolarization happens because, remember, this was full of potassium to begin with. So the cell is full of potassium. Remember, sodium is on the high on the outside. Potassium is higher on the inside. Well, when that sodium moves in, right after that, there are voltage gated potassium channels that open and let the potassium out. Well, potassium's positively charged. It's taking that positive charge out, which makes it more negative inside. So it immediately repolarizes. So this is depolarization. This is repolarization. It goes right back to where it was. Actually, it goes a little bit more negative. Okay, so if we can kind of imagine this happening, this depolarization down here, depolarization, that's the sodium leaking, or the sodium voltage-gated sodium channel open, and then repolarization, that's the potassium rushing out. So sodium rushing in is depolarizing, potassium rushing out is repolarizing. If you can imagine that all the way down, there are these channels all the way down the axon. Okay, and so all the way down you have sodium rushing in, and then immediately after that, potassium rushing out. Okay, and so it's the sodium rushing in that depolarizes it, and it's the potassium rushing out that repolarizes it. Okay, and then of course everything's in the wrong place because you're supposed to have the sodium and the potassium. You're supposed to have sodium high on the outside, but when we just did this, we just let all the sodium in to depolarize, and then we let the potassium out to repolarize it. Everything's in the wrong place, so what fixes that? The sodium, I'm about to write sodium potassium pump. Sodium potassium pump will then pump everything back in place. Okay, so we'll come back and we'll say more about that and the significance of all of this in just a second. Now, the thing is that when this happens, if you've got these lined up all the way along, you're not going to lose any signal at all. Remember, in the dendrites in the cell body, we had a depolarization, but it just sort of faded. This can't fade. It can't fade on this side because as long as you have these channels here scattered all the way down, that means when this one depolarizes, it's going to depolarize the next one, which is going to depolarize the next one, and it just keeps moving down. And so you have this constant repeated depolarization and repolarization events that take place. Okay, so that's constantly going on. Depolarizing, repolarizing. Then it moves down a little bit. Depolarizing, repolarizing, depolarizing, repolarizing, and that is an action potential, and that's what it's called. That's what we're explaining. That's what you have to understand. Sodium rushing in depolarizes. Potassium rushing out repolarizes. Okay, and so the conduction is a high-speed movement of an action potential along an axon. Now, it kind of works like dominoes. And the other important thing about dominoes is it doesn't matter how hard you push this first domino. You could barely tap it over with your finger, or you could, drive a truck into it, and it's not going to matter. That's supposed to be a truck. Um, so it doesn't matter because you knock that first one over, they're all going to fall the same. Okay, and it's the same thing with an action potential. Once you've depolarized this first voltage-gated sodium channel, you're just going to pass it on, and they're all going to depolarize in the exact same way. Doesn't matter how big that first signal was, doesn't matter how much over the triggers or over the threshold you were, it's just going to be boom, 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 all the way down. Okay, falling just like dominoes. So that's actually a really good analogy, the dominoes one, because it also takes into this point of all or nothing. It either goes or it doesn't, or no go. Okay. All right. Same with dominoes. Okay, so let's review kind of, and there are phases of the action potential. First phase is down here, your at resting membrane potential. Remember, you've got a little bit leaky to potassium, but the sodium-potassium pump keeps it kind of in this one area. The leakage of the potassium and the sodium-potassium pump kind of work together to keep it here. So that's your resting membrane potential, RMP. Now, we hit threshold, so some event caused this to sort of approach threshold. We hit threshold, and now, all of a sudden, this is what you have to remember, voltage-gated sodium channels open. So voltage-gated, right up here, voltage-gated sodium channels open, which oops, whoa, I just lost everything. So voltage-gated sodium channels open here. So voltage-gated sodium channels open, and then that causes oops, I apologize. I keep glitching out here. Voltage-gated sodium channels open, and then that causes the sodium to rush in. That causes the depolarization, and then at the same time, the voltage-gated potassium channels are a little bit later. The voltage-gated potassium channels are opening, and that causes the potassium to rush out. So sodium rushes in, immediately afterwards potassium rushes out. It repolarizes, actually goes down here. Remember, potassium wants it to be about -90. So if you give it the chance, it's going to rush out until it's -90, but then they quickly snap shut, and this all goes back to normal, and you get right back to resting membrane potential. Now, how long does this take? Well, this is showing you in milliseconds. It's showing you that it takes about 4 milliseconds. That is incredibly fast when you think that there are 1,000 milliseconds in 1 second. So that means that this can happen many, many times over 1 second. Okay, so if we look at just the permeability, remember, when we initially, sodium is higher on the outside, and potassium is higher on the inside, potassium, potassium, potassium. When we open the channel, we open that first voltage-gated channel. This yellow line here is referring to the permeability to sodium. So sodium channels open first, and then right after that, potassium channels open, and then the potassium channels close. Okay, which means that there's a period of time in here where nothing can happen, and we call that a refractory period. Where there can't be another depolarization. Okay, so if we look a little bit more closely at what's going on with the sodium channel, we can see that normally at rest, the voltage-gated sodium channel, remember this is voltage-gated, it's waiting for that threshold to change. So there's this voltage meter that's actually just a bunch of amino acids that move when the voltage is different, but it's minus 70, it's sitting there and it's closed, okay? So this thing is completely closed. And then when some depolarization event happens, so if we look at this, it's negative on the inside here, and then if we go to the next step, all of a sudden we have some kind of depolarization that's taking place, and so it causes this to open. So these amino acids, and that's exactly what happens, these amino acids move up away from this voltage, and it causes this to open, and now it's permeable to sodium. So this sodium molecule right here is able to move in, and that's going to cause depolarization. So that's threshold. At the point where this thing opens, that is our threshold, which is usually about minus 55 millivolts. Okay, so the sodium moves in. That's what this is showing. The sodium is moving in, which is causing a severe depolarization. Okay, so it's causing it to really depolarize at that point, because now we're letting a bunch more positive. It just became a little bit positive, and now remember this sodium, it wants to move in no matter what. Until it's like plus 65 in there, that sodium is going to continue to move in. And so it moves in, but immediately after that, there's this little inactivation gate, okay? And we draw it like, if I go back to the previous slide, we draw it like a little ball on a string. And if you actually look at the structure, remember this whole thing is a protein. It's actually a little amino acid ball on an amino acid string when you actually look at the actual structure of it. So that's pretty accurate. And so immediately that thing pops up in there and blocks the sodium. And so the sodium can only, because remember, we're only talking about 4 milliseconds total for this whole thing to take place, depolarization and repolarization. So some sodium rushes in, it's like a snap, and then this thing goes closed, and then the sodium can't go in anymore. But the damage is done. It's already depolarized clear up to that point. And then read this. During repolarization caused by potassium leaving the cell, okay, so it's I don't have a picture of that, but there would be another voltage-gated potassium channel that would show that potassium is kind of doing the same thing. Potassium leaves the cell and causes this repolarization, and then everything goes back. The sodium channel goes back to where it originally was. Okay, so now there's an important point. Let's see if I can move this over here. Sorry about that. Okay. I'm having a lot of glitches here, but it's too late for me to start over. Okay. So we have something called a refractory period. So when these channels are opened and the action potential is actually taking place, we know that sodium and potassium are on the wrong side. Sodium is rushing in, potassium rushing out. There's no way that you can have an action potential take place during this period. The channels are open. You can kind of see them drawn up here. It says sodium channels open, and then the potassium channels open. So there's too much chaos going on at this point. And so you have something called an absolute refractory period. It doesn't matter if another signal is coming in. So if you have, here's your neuron, and this is your voltage-gated sodium channel. It doesn't matter if another signal comes in. When this is open, nothing is going to happen. You've already got your action potential that's moving down the cell, so or down the axon. So that's why we call that an absolute refractory period. But then after the sodium channel closes, the potassium channel closes, it starts to get back to normal resting membrane potential. That's what this red line is showing. It's back to about minus 70 again. Okay, so it's kind of getting back to normal. then if a signal is strong enough, if you have a strong enough depolarization signal, you might be able to get it to go. And that's what this graph is showing. It's saying that there is, in this point, at this period, zero chance, no chance of causing an action potential. At here, not much of a chance, but it gets better and better. And this is kind of the sodium, we'll say the sodium potassium pump is kind of putting everything back to where it was. And that's what's going on there. Okay, and then once it's after about 4 milliseconds, it's ready to go completely again. Okay, so why does this matter? Well, and I always usually when I talk about an action potential, I talk about I use the analogy of flushing a toilet. When you flush a toilet, there's a period of time where you can't flush it again. The handle just kind of jiggles, and that's what this is. That's what's going on here. That's that period. That's what the refractory period is. It just can't happen again. Okay, so the goal is to move it in this direction. Okay, so the goal is, this is why we have a refractory period, is you want the signal to move down the axon. And so if you could depolarize a certain area, so it's showing this depolarizing. If you could depolarize a certain area and then immediately depolarize the part of the axon that was just depolarized, if you could do that, then that would cause it to move in two different directions. But because one area depolarizes first, and then it's going to depolarize the next voltage gated. So there's another voltage gated sodium channel that's next to it. And so when this one depolarizes, it's going to depolarize that one. Well, this one that was depolarized before is still in its refractory period. So that means it can only really move in one direction. So we'll come back and we'll look at that again to hopefully that it makes more sense when we actually cover that again. Okay, so so if we go through all of the steps again, the graded potential enters the trigger zone. So if we were to draw this out, we've been drawing this out. The graded potential, that's my dendrites and cell body. The graded potential moves through this area, gets to the trigger zone, which is right there. Voltage gated sodium channels open. This is what you need to know. You need to understand this whole thing. I wouldn't be surprised if this is an essay question. Voltage gated sodium channels open. Sodium enters the axon, which depolarizes it. The positive charge spreads along adjacent sections. So what that means is that, yes, when the sodium rushed in, it went both directions. But it's going to depolarize the next voltage-gated sodium channel. So this right here is another voltage-gated sodium channel. Well, you've just changed the membrane. So that's going to depolarize. Okay, so sodium's going to rush in there, which could potentially depolarize this one, the one that was on the left here, but it's still in its refractory period. So it's going to depolarize this one, and then this one, and then this one. It's going to move down. Okay, so positive charge spreads along adjacent sections of the axon by local current flow. Local current flow causes a new section of the membrane to depolarize, and then we can't forget sodium or potassium rushing out repolarizes the membrane, and that this refractory period prevents it from going backwards. So this is what I was talking about. We start here with the depolarization. Sodium rushes in, depolarizes the cell. That's going to cause this section to depolarize. Sodium rushes in, depolarizes the cell. So it spreads. It spreads. However, it can't go backwards because if this is sharing with this general area, and let's say that it fades as it moves back here. So by the time it gets here with these that are ready to go again, so these are ready, they're ready to go again, but that signal where it's depolarizing right now isn't enough to make it all the way over there. So the only thing that happens is it moves in this direction. So the take-home message is the refractory period makes the action potential move in one direction. Okay. that's how it does it. It does it because this refractory period, because while this is in its refractory period over here, the signal will fade, and the ones that are ready to go never get another signal. So the only ones that are going to be affected by this depolarization are the ones that are in front of it. Okay. So we have sodium depolarizing, potassium repolarizing, and it just continues to move down the cell. Okay, down the axon. Okay, so hopefully you understand that because that's what an action potential is moving down that axon. Depolarization, sodium rushing in, repolarization, potassium rushing out, one direction, the refractory period. Okay, so just a couple of more things and then we're done. Speed of an action potential as a neuron is influenced by the diameter of an axon. Okay, so what that means is we still have to talk about myelin. What that means is that the sodium, the positive charge that moves in, actually spreads out really, really fast. Okay, so let me start over. If we have, let's see, we'll just draw it kind of like this. Okay, and as the sodium rushes in, it's moving, of course, in both directions. Presumably, if this is in the middle, this is still in its refractory period, but it's moving in both directions. And this is just current flow. It's no different. I like to ask people if water conducts electricity. Water only conducts electricity well if it's filled with salts, okay? Electrolytes. Okay, so that means that sodium is moving through this fluid. It's the ion moving through the fluid, and that's current flow. Okay, so when you drop your hairdryer in the water, if it has salts in it, it can shock you. If it's just pure water, it probably won't. Okay, but most tap water has some salts in it, so don't try it at home. Okay, so this signal will fade over time, and that's that graded potential. Now, however, if it's larger, let's say instead of being that big, it's that big, because remember, a lot of this signal is lost by going out the membrane. Okay. However, if it's really big, then it will travel a lot farther. Okay, and current flow, all of that depolarization is going to be faster. So that means a larger axon is actually faster because you have more area and you lose less signal, so you have more pushing and it moves faster if it's a larger diameter. Okay, resistance of the axon membrane to ion leakage, again, if it starts to move out and it leaks, then you're going to lose that signal and it's going to fade. Okay, so what does that mean for myelin? We've been talking about myelin. We talked about the oligodendrocytes, and we talked about the Schwann cells. And so what we can do is we can cover this with a myelin sheath, and that will cause, okay, that will cause the sodium to not leak. So that depolarization event won't leak out as much because it's coated. So that means current flow, which is very fast. So I'm going to put current flow, fast. Okay, so it's traveling at almost the speed of light, like electricity through a wire, very fast. So if we cover that with myelin, what we can do, so let's put a little more myelin. Let's make it go all the way over here. What we can do is we can spread out our, we can spread out our voltage-gated sodium channels. We don't have to put another voltage-gated sodium channel until right there. So that means that this voltage-gated sodium channel goes the speed of light movement almost all the way over to here. We haven't lost signal, so now we have another depolarization event. This one, you can would spread back, but hopefully that one's still in its refractory period. And then we have more myelin. Okay, if I just draw it on the top, and then we have another voltage-gated sodium channel here. And so current flow, fast current flow, and then depolarization. So then what this means, I'll get rid of this mess down here. What this means is instead of having a neuron that's set up like this, where your voltage-gated sodium channels are very close to each other, so this one depolarizes and then depolarizes that one, depolarizes that one, depolarizes that one. If you can block the current flow from leaking out, then you can spread these apart. Okay, so this is myelinated. So if we say this is myelin, what it does is it increases this fast conduction here, recharges it at this point. So we have the voltage-gated sodium channels that recharge it. And then fast current flow again, recharge it again, and then fast current flow again. And so it sort of, so when you're looking at it, it looks like it's going depolarization and then just zips over here, depolarization, then zips over here, and depolarization, instead of just going dump, dump, dump all the way down. Okay, this would be very fast or very slow. This one is going, hits there, and then current flow, and then current flow all the way down. Okay, so I hope that makes sense. And we call this jumping from this node to this node. We call that saltatory conduction. Saltar in Spanish means to jump. And so it seems to jump, this current flow jumps from here to here. And so the more of that current flow you have, the faster it is. Okay, so this might be a little bit more clear. So these are the voltage-gated sodium channels, and we can't forget that potassium channels are repolarizing it, but it's easier to just draw the sodium channels. It shows the depolarization, and this one's going to depolarize that one, which depolarizes that one. And you could have that doing it that way all the way along. But if you insulate it so you don't lose the charge so quickly, you can make it this far. And then the depolarization of this one, current flow, which is fast, will move all the way down here, depolarize, recharges it, and then we have another current flow, which is fast. Okay, so this is, we'll say slow. It's not really slow, but it's slower. So we can put slower, and then fast. And so the more insulation you have, the more fast current you have. And that's why myelin speeds up an action potential. Okay, that's why it does it. It increases this fast current flow and decreases how much of the depolarization. And then of course you've got repolarization. So depolarization, depolarization, depolarization. That's slow. Okay, so I hope that makes sense, because I'll probably ask you somehow to describe that. So if it doesn't make sense, you might want to check your book or send me an email or something. Okay, so so what happens then in things like multiple sclerosis, MS, where the body's own immune system attacks its myelin sheath? Well, that signal will leak out, and that's what this is showing. It's showing that there was depolarization. This came down, but the signal started to leak out, and by the time it got to the next voltage-gated sodium channel, there was no signal, and it was dead. Okay, so that's why demyelinating diseases are so bad, because it, at best it slows it down. At worst, it stops transmission completely, and then this neuron could actually die after no longer receiving signals. Okay. So a couple more things to talk about. I know that I mentioned this before, blood potassium concentrations. Remember, inside the neuron, potassium is at a high concentration. Okay, so potassium's at a high concentration inside the neuron. but it's also leaky to potassium. So I'm kind of reviewing when we talked about resting membrane potential. So potassium is leaking out, but the sodium potassium pump is pushing it right back in. And so what happens when blood potassium is in the normal range, then it sits at about minus 70, which is where it should be. Okay, so when this is all happening properly, and potassium leaks out and then just gets pumped right back in, keeps it at minus 70. And so that means when you try to depolarize it, when you open it up to sodium, it depolarizes it the way it's supposed to be. So this is a sub-threshold graded potential. So this wasn't going to fire no matter what. And this is showing a super threshold. So it goes over the threshold, and as long as everything's right and your potassium levels are where they're supposed to be, then everything is fine. Now, we've mentioned that hyperkalemia. So we've mentioned that potassium levels can really mess with the depolarization of neurons. So what's happened here is this says hyperkalemia. Remember, this potassium was trying to leak out. But if you've raised your potassium levels out here by so much, so even though it won't change the membrane potential that much by this potassium being out here, it won't change it directly. It does change it indirectly because all of a sudden this potassium that was leaking out says, nah, I'll just stay in here. And when you have a positive charge that stays in here, so if it was minus 70, if the positive charge isn't leaving the way it's supposed to because it all of a sudden got crowded out here with potassium, well then this might go from minus 70 to minus 65 to minus 60, and it brings it up closer to threshold. I hope this makes sense. This is resting membrane potential at normal potassium levels. When you increase the potassium out here, all of a sudden what you end up doing is keeping the potassium inside the cell, and that causes the membrane potential to creep up. So here's your new resting membrane potential, and that's bad. That's something that's twitchy, prone to seizures. That's not a good situation. So that's why potassium levels really make a big difference, is because a neuron or a muscle cell could fire when it's not supposed to fire. Okay, a small signal might make it fire, and that's high potassium. What about low potassium? Low potassium can be very bad too. If your potassium levels are low, let's say you're an athlete and you're trying to run or you're trying to play whatever, and your potassium levels are low, well, it's kind of the same thing. Okay, so if you're used to that much potassium being out there, and all of a sudden your potassium levels get really low, what it's going to do is it's going to cause more, this potassium is going to try harder. It's going to want to get out more, taking its positive charge with it, which means that if it was minus 70 millivolts, now it might be minus 75 because this potassium is going to leave the cell. When your blood potassium levels are low, these guys want to move even more because remember they were kind of close to the membrane potential, but yeah, when that concentration gradient changes that much, it's just a mad scramble to leave. And so it might get to minus 75, minus 80, and then you can't get your muscle to fire. And this is why cramps and things like that happen, because you don't have the proper muscle function. You don't have the proper nerve function. You don't have either inhibition, or things just don't act the way that they're supposed to. And so all of your muscles are sluggish because muscles have action potentials too. If your potassium levels drop too much, we're talking about neurons. That could transmit to the brain, and then your brain wouldn't function properly. Okay, so there are lots of very big problems that can come from potassium levels being out of whack. Okay, well, that was long. I'm very, very sorry. I hope it made sense, and I'm sorry for all the trouble I had there in the middle. I might have to redo this someday, but I probably won't this semester, and I apologize for that. Okay.